I had a dream. I always wanted to start a talk like that. It's my chance. I had a dream. I dreamt of doing operations for large-scale applications the right way. So you have a game, you do games here, and you have 2-3 million users a day, you have a lot of errors. And you have to fix them quick enough. And I had a renovation, how to do this better than every tool on the market. And I went on this quest to make this happen in products and tools here internally, and went to walls and despair and disaster and didn't work at all. And then ElasticSearch came along, and I don't want to destroy this suspension. Maybe start with a dream first, and then we come into battle parts later, despair and ElasticSearch, right? Okay, so let's start with the dream. So I had this dream. How did it came to this dream? So when I started here in this company, it was 7 years ago. My first game was this game, Monster World. It's a beautiful farming game. Unfortunately, you cannot play it anymore. We sunsetted this, was shut down just 2 months ago. That was my memory. But basically, it's a farming game. It was a flash game. When the game started, we all at stake everything from the database to the client. And whenever you press something on the game, click a button, basically a REST call would be done on the backend, and then the information then would be saved there in the backend. So we had logic on the backend of the client, and the logic in the backend was mostly to validate what the client was sending. And if it was not sending the right thing, an error would pop up. The game was pretty successful. So at its peak, we had something like 2.5 million users every day. And users clicked a lot. So we had something like 10,000 API calls per second. These are more calls than Wikipedia has, but actually these were changing state in the database. So we had something like 100,000 database writes per second at this peak time. And that resulted in a rather large and a bit hard to oversee system. So we had something like 200 servers, 150 application servers, and 32 database servers. Every one of these database servers was a single point of failure, and I'm the only person to blame for that because I made up that system. Shame on me, but I was also doing on-call duty. You build it, you run it. I woke up in the middle of the night to fix my own network. So whenever we had these client and backend running out of sync, an exception would be raised in the server. And users then would see this. Oops! Something went wrong, no problem. Reload and continue. And most of the time, actually, this happened due to network problems. So 70% of the errors we're having were network problems. I mean, someone playing a flash game in the Philippines might not have the best network connection. Brazil is also another country which is not so great. So basically, if one call got lost, we would run out of sync. Because these calls were not idempotent. It just was not possible in that kind of architecture. So for every user, that might happen every 1 or 2 weeks. Right, that you run into a situation. So not that bad, but overall something like 10% of users every day run into some kind of problems. And that's 250,000 users a day. So that's a lot of noise you see in the log files. So forget about fixing all bugs. It's simply not possible in this kind of system. So besides these network problems, we had 3 main categories of errors. And one was, some hardware outage. I mean, all these single points of failure, the database is failing. But they were kind of easy to detect, not a big problem. For the rest, we had something like, if we had more than, let's say, 50 hours per minute or so, raise an alert. Wake me up in the middle of the night. That worked really well until we had the second category, which were cheaters. So I very well remember this one guy who managed to create 500,000 exceptions in a single hour at 2 o'clock in the morning, 3 times in 3 days in a row. And that brought me to the realization that just checking how many exceptions you have maybe is not the best thing, because every cheater will create masses of these exceptions. So actually what you want to know if an error is important, you want to check like how many users are affected. That is actually the metric you should look after. And it became my quest to convince everyone, including you, that please don't check for the numbers of errors, always check for how many different users are affected. That is a much more powerful metric. Unfortunately, it's also much harder to calculate. So, and the third problem we have, of course, like new version bugs. Yeah. I mean, test coverage in Flash. It didn't help that the project was started with an outsourcing company, then we took over the code from there. That was hell. So the one thing that you need in kind of like operation is fast feedback. So we have a new version out there, and within minutes we need to know if the new version is worse or better than the old one. If it's worse, then we have to roll back or fast roll forward. So feedback is critical. I found a screenshot of this really old system of mine, and behold my HTML and CSS beauty. You see here kind of like on the left hand side, these are kind of like the API calls that we have, and you see two versions. So we were segmenting the users by version or by time, in this case by version. And when you look at this, you see that so this is the old version. In the new version, roughly 10% of users playing, so 7,000 in this 10-minute frame were active, and about 67,000 were running on the old version. And for each of these API calls, then we were looking at two data. So in the brackets, it's kind of like how many exceptions we have, or how many users how many exceptions we have, and the percentage is what percentage of users were these. And that is a subtle thing. Here it's pretty easy, right? So here 28 users were affected, more than 18, so the new version is worse. But here you see kind of like 19 users were affecting the new version and 73 in the old. Still the percentage is higher. So the thing is, by using error rates, you have a normalization. You need to compare different sizes of user segments. And later on, this became very relevant when you do look on mobile operations and do staged rollouts where you launch a new version for 1% of users on Android. You can compare the error rates that these 1% of users have to the 99 of the Android. So this was my holy grail. It's a simple thing, but I wanted this diagram. So I had this, right? So I could show this to people, and it was great. There was just one problem. So yes, I could segment users by version and time, and I could have these normalized user rates, and I could measure users affected. So that means I could compare different times of the day, different times of the year, and also different games, because you have something that you can compare against. So this was my dream. But in the implementation side, this is a system. Actually, there were more applications there, but so I had added one more database. I mean, we had enough, one more. What difference did it do? And to make it run, this was running on Amazon. We used EVS volumes, so there were no solid state disk, anything, and they were running in a RAID 0 configuration. Remember what RAID 0 means? This is exactly. So this is the no redundancies thing. So if one of them, they would never fail actually. They would just slow down. And if them would slow down, then basically the backlog of this database would fill up, and basically that would make the database explode, and after that all the cluster explode. Leading to this. It's a bit of an irony. So the system I managed to measure this caused this. So I was feeling a bit like, yes, I had this kind of like holy grail thing, error rates are the way to go. Yes! But they also put everything on fire. So somehow I could not convince others to do the same thing. Maybe they have something to do with that. So the years went by. I still believed in my dream. I was still on my quest. So in 2013, I then saw my chance. There was a student in town. He was looking for a bachelor's thesis. Yes! I grabbed him. At this time, we had created this new team. before we had backends, so one team was responsible for one game, and then backend developers were part of that team. With mobile games, that more and more made less sense because these games on the backend seem to be very simple. So we created one team to provide services, so to provide a backend as a service to these other teams. So this team, Simple Backend Services, was doing this, offering services like resistance, configuration, A/B testing, containment, whatever. And I grabbed this student to create a new service. So it looked like this. We had a game, it was sending some call, put it in the producer, who then write it to Kafka, which is the queuing system that we're using at the time. Pretty simple, very powerful. Do you know Kafka? Should I explain Kafka? It's okay? Okay. If not, come to me later. You will have some consumer, and that consumer then would write it to PostgreSQL. Pretty simple. The student before was working in the business intelligence team, and they were using Kafka and Postgres. So actually, we were using their system. So at Wooga, all business events, all business KPI are tracked over this kind of system. And then you would just in the browser go there, have a Rails application, and read the data from Postgres. Super simple, super straightforward. Not really error rates in the system, but the rest was fine. So it was like, yes, we had the system, and I was one step closer to my dream, and we really had like this upfront queuing, makes so much sense, it made it robust, so there was no exploding files everywhere anymore. That was good. We managed not only to track errors and crashes, but also like info statements, debug statements, even have a live view of the debugs that were running through the system, because in Kafka that is easy, and even added a full-text search. And we learned that, hey, having a full-text search of errors, that's a really nice thing. I mean, this, of course, was this like percentage thing, full-text search, but still it was nice. So, yes! But it was a student project. He was working 6 weeks on the code, and then he moved on, and yeah, test coverage. Not there yet. I was so close. Not there yet. Next chance. 1 year later. The lab time system. What's lab time? At Wooga we do games, and most games will just fail. So that's just reality in the market. 90% of games kind of like, we stop sometime in production because we realize that they don't work anymore. At least we did it at that time. And lab time was something that when you start a project with some backend developers on it, when you start a new project, you don't need backend right away. So what do the backend developers do in between? Lab time. So we have 2 lab times at the moment. One set off to fix my mess in Monster World. Nice of him. And one I could convince to build me my system. And this time even a screenshot. So this is how it looks. Memories. Isn't this nice? Kind of like, so we see here kind of like, this is the numbers, percentage of users who had an error in that version. We could see this over time. We could basically group errors by name and stack trace to see like what users, what errors are distinct. And when you zoom in a bit, you also see like that we have how many occurrences, so how often this exception or this error happened, how many users were affected, and what percentage of users it is. So I had my error rate. Finally, I was so close. Actually, this kind of system is very hard to build. Because when you have error rates, it's not only the error events that you need. So whenever someone had an error, you also need to know how many users did not have an error at that time. Right? Makes sense. So every time someone started playing a session, and every user did this maybe 10 times a day, they would need to send a call to our backend to say, hey, I'm here. So that we know like how many users were playing the system, so we can calculate this percentage of users. And also this calculation of percentage of users is not a trivial operation. Good for us. There was a white paper. We love white papers here. And this white paper was about hyper-log-log. That's a probabilistic algorithm, actually from 2007, but Bloom filter was in vogue in 2013 year, and we implemented it every game, everywhere, and hyperlog made it to us in 2014. And I think I need to explain this a bit what this does. And I'm borrowing some talk from Twitter here, who had the same idea. In 2014, they implemented Crashlytics answers based on hyperlog. So hyperlog, the problem is, let's imagine you have 1 billion device IDs, so unique identifiers for a device, basically your users. And if you want to store them all in one set to see, like, is this user in a set or not, so you want to have the counter-cardinality of that set, then you would need something like 10 gigabytes of data. With hyperlog, you need 4 kilobytes. But you sacrifice some accuracy for that, because it's a probabilistic algorithm, a very cool one. And it works like this. So you would take the device ID and would take a hash out of it. So MD5, whatever, created something like a 64-bit of that. And in that bit set, then would look for the longest consecutive row of ones. So you don't remember the whole bit set, but you just make like, okay, in this case, we have 4 ones, so we could calculate 4 out of this. And for every user ID we put into this hyperlog, we just measure like, which was the highest number of consecutive ones we ever saw. It's a bit like, let's say, I give you a coin, and you toss the coin. And heads is the 1 and tails is the 0. And you throw them up and down the whole time, and you count like, what was the longest streak of head you got. And after some time I come back and you tell me 3. The longest row of heads is 3. Then I know that probably you run bored after 5 minutes and stopped. Not very long. If you tell me 20, boy, then you were tossing the coin a lot. And it works like this, so basically it's an approximation how many different user ID you stuff into that thing. The problem is, the very first that you stuff in might be all ones. And then you get a completely different result. So they use something like bucketing. They use the first bits of the bit set to determine which bucket it is. For example, if you just use the first bit, then you have 50% of device ID go into bucket starts at 1, and 50% starts at 0. And if you usually take something like this first 16 bits, so you have 65K of buckets, and this outlier, like everything 1, then would affect us only 1 of the 65K buckets. So then you take a mean and you get an approximation. Did someone understand this? If not, I can pass them on the link on the Twitter thing and some blog post, or I'll try to explain it later. The thing is, this is a very clever thing to not use up much memory and CPU consumption to find out how many different user use it. It's basically a distinct count aggregation. And very fast. You sacrifice some probability, you might be off in the numbers a bit. So, we read that white paper, or the lab time guy read the white paper, and we set out on a quest to build that system based on that. How cool is that? It's a lab time. So, here at Wooga we do a lot of stuff in Erlang, and he chose Erlang as a system. So basically in Erlang, you can spawn a lot of processes. A process is a bit like a thread in a JVM, but it's much more like this. So it's no problem to spawn 100,000 processes or more on a single machine. Each one has its own garbage collection. It's highly concurrent. In this regard, it's super powerful. That follows the actor model. Someone knows Acker, they borrow from that. So let's say we have a request with the new device ID, and you would spawn off a process that would keep this hyperlog structure in memory. And different calls would go to the same hyperlog. So we just need something like 4 kilobytes in memory for that stuff. And this is stateful in memory, so it's fast. And if you stop sending requests to that thing, then you get a timeout after some time. That's part of the Erlang OTP framework. And you will just dump the number we have to disk. And this hyperlog could represent, for example, the number of distinct users in a day, or minute, or second. So you store different counters like this. And After some time, this process would die. If a new request comes, for example, to read this or to write something else, we would spawn the same process again. We would look on S3. If we find it, we store the state and continue. So this is how basically a stateful session, the stateful concept. This is how we, by someone like most of the world, where we had 150 application servers before, we now do this 5. It's this kind of powerful concept. And for every error, we would have different counters. So imagine like you get an error event in, then it would update 3 counters. So one for the count day, one for the count hour, and one for the count minute. Actually, it's a bit more clever than that. So you get these masses of events in the system, and you will just update 3 data structures in memory, which are 4 kilobytes each. That's awesome. That's really fast. And if you put this whole in the system, it looks a bit like this. You get this request in a process. That process spawns off a group process that manages the group. So that's basically the information for the error that have the same name and stack trace, which follows the same process. So you spawn it off, but this time we would dump this to DynamoDB so we can do some extra operations. So we would store, for example, stack trace whenever only once in the system and not 500,000 times if it's a mass error. And this group process would then be responsible to spawn off these counters or the multiple counters to return. So this is a system that is basically modeled after Twitter Storm. It's kind of a classic real-time processing system. And it's pretty cool stuff. We benchmarked this and it just worked. Nice. Really cool system. And of course, this needs to run in a cluster because we have the Erlang work and we need more than one machine to handle the load. And the interesting thing is how this cluster works together. So let's say we want to update a group on the first server here, but the request ends up here. Then we need to know, okay, we need to update the group process on the other server. So in the Java world, you will use something like Zookeeper based on Paxos algorithm. We had our own implementation called Locker. That's an Erlang open source framework that we created. And this Locker process runs on every machine. And basically, this one process is aware, like, okay, which error is managed by which machine. Because whenever you spawn off a new group process, we would register there. So this guy here knows that the group is here because this group registered here. And then it would just send the data to that group. That's how a cluster works. So basically, you can ping any node in the cluster, and the data would get magically that belongs to it. And of course, it also works the other way around. Isn't this a beautiful system? It's magnificent. I mean, what could possibly go wrong with a system that awful? Awesome. It's amazing. 2 things changed after we finished, or the guy and one from the team, a junior, finished the system. First of all, okay, how does the system look and hold? So we have a load balancer in front, which the game sends it to, and it's distributed in line. How do we display the data? I forgot that part, sorry. We have a browser, same thing. We had a single, because we never used a single JavaScript app before, so we had to use one because it's hip, so we used Angular. And Angular would talk to actually one of these machines who had a different role, and this would then in fact identify basically the group where to retrieve the data from. So this is the system that looks like, and this is magnificent, and nothing could go wrong. Of course, because I mean, this was a really simplified version of explaining the system. It took me some days to find out how it worked. So what could possibly go wrong with the system? Actually, 2 things happened. So first one, we launched a new game. This is a mobile game, and it was the biggest launch in Google's history. So we knew exactly when to start it. We had a hype campaign, PR campaign running up to TV advertising, whatever. So I think we have something like 3 million installs over the first weekend. And this game had one thing that we did so often before. It was running on Android. Yeah, that was good and bad for the system. We come to that in a second. And the second thing is, remember, that was a lab time project. And lab time projects are temporary. So exactly when this project came along, and what he built was becoming more and more important, the most important thing ever, this guy left for another team. So the simple backend services team, who are used to dealing with persistence and other systems, they suddenly inherited this system just the moment when it becomes really important. And we had three problems in the system. And the first one, just basically, there was no upfront queue. So whenever we had one game, a new version of that game in soft launch went amok, and the whole system was just crashing down immediately. Yeah, we fixed that. We didn't put Kafka on top, since we were running Amazon, we put Kinesis on top, but basically same setup, have a producer write it to a queue, and the consumer then puts it into the system at a rate that the system can contain. Simple. That one was easy to fix. The second one was not so easy to fix. So we had this highly distributed, really cool online counter system, this one here. And the problem is there was a lot of intra-cluster communication. Because of these counters, in the end, we had more than 1 million of these processes running around in the cluster, and everyone wrote it to their own S3 file. And every request updated only 3, but when you were trying to read, then you might read something like thousands. Also, we had some nasty little hidden bugs. Did you ever debug distributed network code in a system you didn't write yourself? That was fun. It took us something like 2 weeks, the whole team, just to find this bug. And the whole system is kind of like, you had kind of like load waves, so one node in the cluster got out of sync, and then kind of like the other service in the cluster got out of sync, and then the whole thing came crashing down, and in the end, we just removed all the intra-cluster communication. So what we did is we said, every game resides on one of these nodes in the cluster. This is, by the way, exactly the same way how New Relic does it. They only, at least up until this time, they only had 8 servers in 2014, and every user would reside only on one of these machines because they were heavily efficient. Probably using the system like that. So we just completely removed the intra-cluster communication, used some kind of static sharding, like this game goes to that box. Reduced complexity a lot. And suddenly we could mostly run the system. But the third problem was a tough one. And we were assuming that for every event that comes in, the number of counters you would write follows the order of magnitude of n. It's linear. So 3 or 5 counters that you would write. And the whole system was based on that premise. And if that would have been true, it would have been an efficient system. Unfortunately, when you look back at these slides, maybe you noticed this. Here we are comparing 2 versions. So of course, then we need to have different counters, right? So we need to calculate the number of users affected of version A and of version B, and of course it's more than just one version. It becomes even worse. You notice this one here? That's a faceted search. That's many different dimensions. So we thought it would be like this, but in reality, that was being multiplied by dimensions. So we not only updated 3 counters, but 3 counters per version, per operating system version, and per every fucking device. And we are talking about an Android launch, we had more than 5,000 of them. So instead of updating 3 counters, we updated something like 20,000. This is actually more a read case, but basically it was unbearable and very tough to handle. And I mean, also in the UI, we could combine these. So you could select one version, one technical version. So we also needed to store counters for the combination of these. And when we did queries to the system, and these counters were not in memory, it could happen that one query, then one user had something like, we were starting like 100,000 processes at the same time, and the server would run out of memory. So doing the wrong request could run out of memory the whole system, and then it would come crashing down. So, yes! I had my system! And actually, we managed to manage this Android launch. And without this system, we would not have been able to do that, because at that time for Unity there was no service available. And by these kind of like different counters, we would find out like, okay, this is a bad device. It has only 16 kilobytes of memory, so we won't ship to it. So we could exclude them from the launch. And that was critical for the success of the launch. So in that sense, this project was successful. But it felt like this, it was firefighting the whole time. So we had something like, to make the system fly, I think there was something like 3 person months to build the system, or maybe 4. And then we spent another 10 to fix it, to make it running, because we committed to the system, we had this launch, and we had to make it live. Actually, we set ourselves an internal deadline for, I think, 1st of December 2014. If you couldn't fix the system, we would put everything away and just wasted one year of work. We fixed the system or made it barely stable 2 weeks before that deadline. So it was really close. But my dream was still alive. Somehow. Somewhere behind this. But there was something else. You see the screenshot? Look around, do you see it? A search box. In the student prototype system, we had learned that full text search is cool. And isn't there these full text thingy around? I remember, like, I mean, you probably remember 10 years ago where we did this Lucene full text search for people. I remember that. I said, like, full text search would be cool. Could we add something like just a search box or something? And we did. So we took this system, after we did it, and just would write everything, every event that we would get, every call that the system would get, we just would write down to ElasticSearch. So at peak, I think, something like 1,000 per second or so. And it just worked. Okay, cool. So then we had the search box, Angular, so we just had one more call here. So this was still the majority of the system, but full text search moved to here, and this system had exactly the same data as this one. Wow. And we did the most simple thing we could do. We just chose one hosting provider. So they were called found that way, now it's Elastic Cloud. Just picked something that we have 2 servers. So we have 2 servers and 2 availability zones at Amazon, and 1 tiebreaker for the forum. And for every day, we would just start a new index. We would have 14 of them, 14 event spots, so 14 indexes. Just worked. Amazing. So easy. So for me, it was really a surprise that we made all this effort and all this pain and really, really professional persons working asses off to make this fly. And the same amount of data, we just dumped it, this just flies. No optimization whatsoever. We just dumped it in. And then we read something, you might guess this, white paper. I actually heard of a white paper called Hyperlog clusters. Or actually, where we heard about that was in a blog post from Elastic, because they implemented Hyperlog clusters in ElasticSearch. And basically what it does is, it uses the same principles as Hyperlog, but not when writing the data, but when reading it, on the fly, on demand. It just works. So basically you have a different aggregation layers. You can have a kind of like this thing count that is unique, and then you really count everything, and it's slow. Or you can say like, do this aggregation, and it uses, what's it called? I forgot the other algorithm, and if the data set gets bigger, it uses hyperblock plus plus under the fly. So basically what I just described to you, it does on the fly, on demand, while doing the query. Interesting. So we played around a bit with Kibana. And the use cases we had in our UI with the old system, and it didn't crash the whole system, we tried that out in Kibana. And guess what? Just that. Fly, so filtering by device, standard faceted search. And this is something I did this morning just to get screenshots, but it just worked. Interesting. So, while we were so in pain running the old system, so we did something drastic. So we created the new system, the system 2.0, and this time everything was going to be better. Promise. Use this system and just cut out all that stuff. Just delete it. And that would have been great. But this is the system 2.0. And do you know this 2.0 syndrome? You want to make everything better because now you want to know. So we replaced Angular by React. And this is a team, there's no JavaScript developer on the team. One half, he later left the team. And React is really cool. I believe it's a very powerful system, but these are folks who really know how to run Amazon service or root an operation, who know Erlang and Ruby and know JavaScript. And for them, React was a bit hard. And we just had a small rates application to just host the React application, and then basically everything was React. And it looks beautiful. So it still runs. So I just need to show you how beautiful this is. So this is now live on our system. So this is one of our live games. Okay. Let's see if that works. Aha! So, well, now it's interesting. Oh, I see myself here. So it's a really cool thing. So it's a really nice React application. So that's the live view of one of our games, one of our medium-sized games. It's a lot of warns, no errors. And of course, because we need to be really cool, it's all one page. You scroll down. And if you click on one error here, I don't see what I'm clicking here. Then you scroll down, of course. You can use the mouse to skip through the errors. So these are all real-time queries to ElasticSearch and an index that have a few 100 million records in it. And it just works. And it's really cool. You can even close something like drill down, like, no, I don't see anything. Let's see, I want to see all bugs by this operating system version. I think I have to click here. I can't see anything on this screen. Yeah, I can't. I don't know how to zoom in. And the thing is that because this is all one page and it's React, we managed to build so many bugs in it that we no longer know how to fix them. So basically we added a filter here, and if I do the same filter manually, I get different results. And lots of other things. So it's a really cool, nice system. It's beautiful. I mean, look at this. It's amazing. You see like versions and compare like which one's better and all that. And it's just an amazing system. So where's my mouse? Here's my mouse. Okay. So much for. Now I managed to clear stuff. So, do you know the game Find the Mouse? Yes, it's it. Okay. Yep. So it's a beautiful system, and we're actually just 2 weeks away from marketing this professionally to other companies. But the reality is that for us, for this team, it was super hard to maintain. So, yes, success. The system really looks beautiful and does fulfill all the requirements. Just this team was not able to sustain it. So bug fixes or feature requests in that thing. So the first system we should also have on the foot of the back end, you should also have on the foot of the front end. So coming to the last system of today. And I really like this acronym KISS, especially the second S. So we had the system, and ElasticSearch was just working beautifully. It just did work. So we kept exactly the same backend and put a new frontend on top. Very simple. So we just used a plain Rails application. Because for this team, that was easier to handle. It's not looking that beautiful, but it just fucking works. And this is how it looks like. It doesn't look as beautiful as the other one. Let's see if this time it goes better. So this is a beautiful version. This is a new version. Android production. It's a tad slower. We have some filters in here that say only hours inflated. So basically, you have a classic faceted search on ElasticSearch. This game has, I think, something like 300,000-400,000 users a day. And when you click something, then you open a new page. No fucking endless scrolling. Have some data here. You can also go in here. Go through the bugs. Have some charts. Basically the same thing. So let's see if it works this time. Aha! Learning. So if you want to know more about system, I can show you later. So it has the same functionality. It's not that nice, probably not nice enough to make other customers pay for it or whatever, but it's good enough for our internal use cases, and it's easy to fix fast. So the system now is capable of processing something like 9,000 requests per second, so that's the maximum that it can do. But we have a quota for each individual game of 1,000 requests per second. So this is something where we have the quota on the producers. If we have more, we just start dropping requests. So we protect our system. Something that we also learned the hard way when one game started spamming us. That's 5,000 requests per second. That was not so fun anymore. It just works on these two servers, as I showed you, because it's exactly the same backend. We didn't change anything on the ElasticSearch backend. We just stored it for 40 days, and for every day we have something like 20 million events in the system with a total size of 30 gigabytes. So, actually interesting enough for us in this ElasticSearch system, we are not CPU bound or memory bound, we are disk space bound. So the 500 gigs of data, roughly, that we have. That's all limited. When you look at all the data that we have in here, so these are the individual games. You see, this is for 30 days. You see these daily spikes that we have in here. And for 24-hour periods, this is how it looks like. So you see these two different calls that we have to start events. So that's every user starting a session. And these are then the errors that we have. So around about something like 20,000 calls per minute is what the system does now. But if you look for the last month, you see these outliers here. Remember, very early in the beginning, like one of the error causes is bugs in a new version. Please read the bugs in the new version. But since we have a queue in there, this is a delay time. So this is how old the records are that we insert into Elasticsearch. And basically it's a flat line, and if some game really misbehaves, then we maybe have a delay of something like 10 minutes. But the rest of the cluster doesn't work. So wrapping this up, before we get to the bagels upstairs, at least I want one. Are there some left? Maybe. So for me, this is the time currently to look back. I will leave Wooga after 7 years. Actually, Friday is my last day here in this office. And start something new then in 2 weeks. And while doing the talk before and now also this talk, it was kind of like to reflect and look back, because this was also for the quest and a journey for me about 5-6 years. And one thing, even with all the pain and all that, using error rates is now the way how we do it here at Wooga. Maybe now Crashlytics caught up, maybe we switched to using an external service, but this is the way how we now do operations for our games. So one of the wrapping up for me is kind of like believing in your dreams, be consistent about it over the years, even if you have this pain and fuck-ups. But that's for me like one of the main takeaways of this. The second one for me is the solution that you build need to fit to the problem, of course. Right? The first real-time processing thing, it was an awesome, amazing thing, and it really worked. It was a brilliant engineering mastery. But it was not fit to the problem, because when Android came along, kind of like the whole premises were exploded. But the second one, I mean, that's we all know, right? I mean, that's true. You have requirements and good systems. But the second learning for me is even more important, because it was not so clear to me before. The solutions that you build, they also need to fit to the team maintaining the system. Also true. But at Wooga, we have kind of like a culture of like, everything we knew, we innovate and do something new, and we just overdid it. This mimicking Twitter storm is really cool if you're Twitter. If you're not Twitter, maybe you should not try to build a system that Twitter built. Which brings me to the last one, which for me still is amazing. So we had this brilliant system, engineering design, and worked our asses off to make this work. To think about it, argue about it, with many bright people, and to just replace the backend by some hosted service named ElasticSearch, and it just did work. And for me, allowing me to build a system that is more simple, that is more elegant, that upholds really the value of KISS, like keep it simple, stupid, and the stupid is most of the time to myself, is something that I really admire and really proves to me the value of solutions. So for me, ElasticSearch really is amazing, because it allows me to do that, to simplify a system by orders of magnitude, and it still works even better than before. So for me, my summary is just ElasticSearch. If you have questions, now's a good time to ask them.
Okay, thanks for the talk, great insights. You said you save 20 million records per day. Mm-hmm. How performant is the full-text search of ElasticSearch for you?
No problem whatsoever. I just did one. I can show you later on. So it depends a bit, like, so for a larger scale, you might run something like maybe 5 seconds or so, but as long as for the smaller games that only make like so it's pretty enough. So I would say that usually it's below 2 seconds. So it's not like the logs that you go like and do a try like for maybe a minute. It's not the case, because data is very structured, and I think it's also due to the way how we do this, but no problem in this regard.
How big and complicated or simple are the event structures that you push through?
It's very simple. It's basically, so we have a REST API where clients do a post, which is basically a hash map of key value pairs. And some of the values can be pretty long. For example, you can log something like breadcrumbs or metadata or stack traces. And most of the time it's very easy to use, like I think bicep or so, but all this is a flat hash map. And this is basically the structure that we have also used. Yeah,
So
event
this is what
documents.
lands on an Elasticsearch.
This is an Elasticsearch.
Right. And can you maybe share some order of magnitude, like, I don't know, 10, 5, or like 100?
How many files? There's so many, how many fields in this
Yeah.
thing? I think for the something like 20 keys or so it's 15 to 20 keys, and then maybe 3, 4 large ones, like the breadcrumb, which can be a few K.
Okay.
But something. So overall, pretty small documents compared to what you usually put in photos.
Yeah, you built your own UI to query. Did you look at Kibana or you did the freedom of your own software?
So we use Kibana internally, and also from time to time we give access to our developers to, if they really want to go down, and we also use it for prototyping. But we did not really consider it to make it publicly available to everyone, because then we feel like for different queries we could then kind of like affect everything. But most of it, actually for most parts, we don't want to spend time educating everyone in the system. So we decided to have an opinion on what matters and what not, and to put that in the UI and put it in front of our users. And we use Kibana then if you really need to dig data later, but then it's probably more like one of us and one of the game teams to dig in the data together. Anything else? Or is everyone hungry?
Do you have some kind of grouping errors, like single errors?
So basically all the errors, they are grouped. So for a criteria, so the consumer actually creates a hash out of, I think it's the name of the error, which is usually something like the null pointer exception or whatever, and the hash of the stack trace, or both together in a hash. And that we use as a unique identifier, both for the navigation in the UI, but also to store as a document. So basically this identifier becomes one of the field of the error occurrences of the 20 million. And then we can basically then aggregate them, all that have the same on them, do a distinct count for users to get the error rate for that. It's pretty simple. So it's a flat thing of every error event, that the only thing is you put in this group ID so we can later on group them. And the group is just a hash. It's super simple actually.
Are you hosting Amazon, using Amazon ElasticSearch?
The question is if you're using Amazon's ElasticSearch. So the current version is version 2.2. Version 2.3 would use Amazon's ElasticSearch instead of Elastic I/O solution. So right now we are not using Amazon. All the application servers are at Amazon, and also Elastic hosts them at Amazon. The reason why we will switch is that the standard service sizes provided by Elastic are pretty much one size, and you can just scale them up. And because we need a lot of disk space, we are way overpriced in terms of CPU. We have maybe 20 users using the system, and you could do it with way less cost if you just would have more disk space. So we will probably switch over to Amazon's Elasticsearch solution because of that.
What instance types are currently in use for the node?
Big ones. I think the whole thing, it's the 64 gigabyte RAM, 2 of them, so I think total cost is something like $3,500 a month. If you're on Elastic, and I think with Amazon it's easily half or a third of that. Just didn't get around the time to do the migration. I'm hungry. You too? Let's go eat. Cheers.